Hello everyone, my name is Kalef. Now I'm going to present the work whose title is Deep Learning Based Specklegram Strain Sensor with Extended Dynamic Range. As we know, coherent light propagates with different reflection angles inside the core of a multimode fiber. And because of that, interferences occur among the modes, which can be constructive or destructive. As a result, when the light emitted at the end face of the fiber is projected on a screen, a circular pattern is formed. This pattern is called specklegram or speckle pattern and carries information about the current status of the multimode fiber, which means that the spectrograms are sensitive to the physical perturbations applied on the fiber. Such a sensitivity is explored in diverse applications for measuring different physical parameters and in diverse areas of science and engineering. The setup of a fiber spectrogram sensor is simple and can be designed using components of relative low cost, including a coherent light source, a multimode fiber, a coupled charge device camera, and a computer for running the algorithms involved. Regarding the interrogation process of the fiber spectrogram sensors, correlation techniques are used to evaluate the spectrogram's variation and associate them with the physical parameter to be measured. Among these techniques, we can highlight the normalized inner product coefficient, the NIPC, widely used in the literature, and the zero mean cross correlation, the ZNCC, matching technique that presents an invariance to uniform brightness variations. However, in spite of the high sensitivity, this sensor has a limited dynamic range due to the saturation of the correlation technique. As we can observe in this graph, the region of saturation makes the calibration curve to lose its linearity. In this sense, this work proposes a fiber specklegram strain sensor based on a model trained through a convolutional neural network. The training is carried out using a dataset composed of spectrograms previously processed through image processing techniques. The resultant intelligent model plays the whole of an interrogation system and accomplishes the calibration of the sensor, which results in a sensor with extended dynamic range and high sensitivity that is capable of measuring axial strains applied over a polymer optical fiber. Well, regarding the experimental setup, the, the presented setup is used to acquire the spectrograms, and such a configuration employs a linear step motor to exert precise axial loads to assess the strain sensitivity in a section under test of a polymer optical fiber. In this video, it's possible to see the sequence of specklegram frames acquired through the setup. Regarding the step-by-step of the proposed method, first of all, a region of interest of size 81 per 81 pixels is defined for each frame, Then the images are converted to grayscale and the noise through a 2D discrete wavelet transform. After a pixel downsampling is performed and posteriorly a targeted curve is defined. Finally, the dataset is subdivided in training and validation subsets for performing the training through the convolutional neural network, and the resultant model generates an output curve, which is used to create the calibration curve of the sensor. The targeted output curve is an important thing for the method. This curve is based on the behavior of the axial strain applied on the fiber during the controlled experiment. The curve is composed of ideal values of hypothetical correlation measure applied on the frames, and as if the first one is taken as the reference. So such a curve works as a desired output for the convolutional neural network. Concerning the CNN architecture used to obtain the regression model, this architecture is composed of an input layer followed by 4 convolutional layers, where the first one has 16 filters, the second one 32 filters, and the 2 others have 40 filters. All the filters have a size of 10 per 10, and the batch normalization between consecutive convolutional layers is accomplished, followed by a rectified linear unit, which is used as activation function. So at the end of the network, a fully connected layer of size 1 precedes the regression layer. This architecture was chosen after testing many different configurations. Regarding the division of the dataset in training, validation, and test subsets, 2 configurations are adopted. The first one is called uniform dataset division. And in this configuration, for every 100 frames, 50% are used for training, 30% for validation, and 20% for testing. In the second configuration, which is called concentrated dataset division, the first and the last 200 frames join another 200 frames of the middle of the dataset to compose a subset of 600 frames. And from the subset, 400 frames are randomly chosen to form the training subset, while the other 200 frames are used as validation data set. And the remaining 500 frames are used as testing subset. Well, concerning the results graph, in graph A and B, we have the curves generated by evaluating the frames using the ZNCC and the NIPC. The dataset of 50 per 50 pixels is used to obtain such results, where the first frame is taken as the reference. The graph C The graphs C and D contain the calibration curves obtained via the CNN model. In graph C was used the uniform dataset division, and in graph D was used the concentrated dataset division. In all the calibration curves shown here, the linear fitting curve is plotting over the full dynamic range. In addition to the R2 score, the dynamic range size and the resultant sensitivity are shown in all the graphs. Comparing such results with the results of the ZNCC and NIPC curves, the conventional techniques, it's noted an increase of approximately 35.6 microstrain in the dynamic range of the CNN model curves in comparison with the dynamic range of the ZNCC and NIPC curves. Another improvement can be seen in the R2 score. The calibration curves generated by the CNN model presents a higher score, which indicates an improvement in the linearity of the calibration curves. In addition, the proposed approach maintains a high level of sensitivity. Therefore, we can say that the proposed technique successfully extends the dynamic range and improves the linearity of the curves and maintain a high sensitivity compared with other conventional techniques. The novel approach makes it possible to design a sensor capable of estimating with high sensitivity the axial strain values applied over a polymer optical fiber. And on behalf of all authors, thank you very much for watching.